Chapter 1. The Foundational Crisis of Numeric Origin and the Necessity of Supersymmetric Zero. The foundational misunderstanding at the heart of modern mathematics is not trivial. It is not a mistake in notation or a matter of philosophical preference. It is a structural mischaracterization of zero itself. Mainstream mathematics defines zero as the absence of quantity, a placeholder, a null value, or simply nothing. But this framing is catastrophically insufficient to explain the generative role that zero actually performs in the emergence of all numeric structures. When we define zero as mere absence, we overlook its potentiality, its symmetry, and its capacity to function as a source state, one capable of giving rise to all numeric forms by well-defined mathematical mechanisms. This error is not confined to elementary arithmetic. It permeates calculus, linear algebra, and the mathematical infrastructure of physics. The result is a cascading instability in our models of emergence, causality, and origin. No coherent theory of numbers can begin with numbers themselves, just as no theory of spacetime can begin with localized points without postulating the continuity that gives those points meaning. If we try to ground number theory in numbers, we encounter the same recursive paradox that appears in naive set theory, the infinite regress of nested assumptions. Let us examine the problem with mathematical clarity. If one proposes that the origin of numbers is simply the number 1, we must then explain where 1 came from. If we say it came from 0 and define 0 as non-existence, we contradict ourselves, because non-existence cannot causally generate existence. If instead we treat 0 as a number in its own right, we once again run into regress. What generated that number? What distinguishes 0 from the hypothetical pre-0 or the undefined space from which 0 itself must have emerged? This circular logic does not yield a valid explanatory chain. It only delays the question of origin. The attempt to resolve this by appealing to pure abstraction is similarly inadequate. Some have claimed that numbers just are, that they exist in some Platonic realm, independent of causality or process. But this view does not provide a mechanism. It gives no account of how numerical structures emerge within physical systems or computational frameworks. It severs mathematics from reality rather than illuminating it. What, then, must the origin of numbers be? Logically, it must be a state that is not itself a number and not non-existence, but something different altogether. It must be a condition that contains all numeric possibilities in an unexpressed, undifferentiated form. In other words, it must be a maximally symmetrical possibility space, a field of potential that does not yet exhibit contrast. It is not a void, but a totality in symmetric superposition. We therefore introduce the formal concept of supersymmetric zero, which we denote by the symbol capital Z. Z is not the digit 0. It is not the empty set. It is a mathematical state of perfect numeric symmetry. Every possible number exists within Z in equal amplitude, unexpressed but latent, awaiting differentiation through a collapse mechanism. This collapse is what generates numeric distinction. It breaks the symmetry of Z and gives rise to particular values. To formalize this rigorously, we turn to the mathematics of quantum mechanics. We construct an infinite-dimensional Hilbert space, which we denote script H sub n. This is a complete vector space equipped with an inner product, where each basis vector represents a possible number state. The basis vectors are written in ket notation as ket n, where the variable n takes values in the set of natural numbers, including 0. These kets form an orthonormal basis. That is, the inner product of ket m with ket n is equal to 1 if m equals n, and 0 otherwise. In this space, each ket is an eigenstate of the number operator, which we write as n hat. Applying n hat to ket n returns the scalar n times ket n. This establishes that the operator n hat assigns each basis state its corresponding number, and that the set of these kets spans the full space of discrete numeric values. We now define the supersymmetric zero state, or ket Z, as a coherent superposition of all these number states. Formally, this is written as ket Z equals the sum from n equals 0 to infinity of C sub n times ket n. In speech, that means we take each numeric basis state, ket 0, ket 1, ket 2, and so on, and assign to it a coefficient C sub n. We then add them all together to form the state Z. But these coefficients are not arbitrary. They are strictly governed by two critical requirements. First, the superposition must be normalized. That is, the sum of the squared magnitudes of all the coefficients must equal 1. Mathematically, this is expressed as the sum over n of the modulus squared of c sub n equals 1. This ensures that the total state has unit norm in the Hilbert space, in accordance with quantum theory. Second, and even more important, the coefficients must exhibit perfect symmetry. This means that the absolute value of each coefficient must be identical to every other. In other words, for any pair of indices m and n, the absolute value of c sub m must equal the absolute value of c sub n. This symmetry condition guarantees that no number state is given preferential weight. The zero state Z thus embodies maximal entropy. It contains every number, but with no bias toward any particular one. From these constraints, we derive the explicit form of the coefficients. Each coefficient c sub n can be written as a unit magnitude complex number, specifically e to the I phi sub n, divided by the square root of capital N, where n is the number of terms in a truncated version of the superposition. The phase factors phi sub n may vary, but the magnitude of each coefficient remains fixed. The choice of phases can be optimized for various mathematical properties, such as minimizing entanglement entropy or maximizing orthogonality in composite constructions. However, working with an infinite number of terms introduces mathematical challenges. Infinite series can diverge. Norms can become ill-defined. To address this, we use regularization techniques, the same tools employed in quantum field theory to tame infinities in particle physics. Specifically, we apply dimensional regularization, which involves analytically continuing the space to non-integer dimensions, and then extracting a finite value through controlled limiting procedures. We also use analytic continuation to extend the domain of convergence and define otherwise divergent expressions. Using these tools, we define the regularized supersymmetric zero state as follows. We first construct a finite sum. We take the first n terms of the superposition and compute the vector. We then normalize it by dividing by the square root of the sum of the squared magnitudes. Finally, we take the limit as n approaches infinity, ensuring that this limit exists in the strong topology of the Hilbert space. This yields a well-defined, infinite-dimensional state that maintains both normalization and perfect symmetry. This is our mathematical reconstruction of zero, not as emptiness, but as totality without differentiation. It is the ultimate seed state, containing all possible outcomes, all numeric structures, and all mathematical forms, in a single balanced configuration. When symmetry is broken, either by measurement, interaction, or collapse, this seed unfolds into the full landscape of numbers, giving rise to arithmetic as an emergent structure. In this framework, we no longer need to ask, where did the numbers come from? Numbers are emergent features of collapse operations applied to a supersymmetric ground state. They do not pre-exist that state. They arise from it through mathematically well-defined processes. This resolves the regress problem. It dissolves the paradox of creation from nothing, and it anchors the entire edifice of mathematics in a rigorously constructed, maximally entropic origin state. This is not a philosophical speculation. It is a concrete, operator-based, mathematically exact account of how numeric structures arise, from zero, not as void, but as supersymmetric in differentiation. And it forms the foundation for a new ontology of mathematics, where emergence, contrast, and computation all begin with the physics of Z.